So let's look again at those three cases that I put on the previous page of the improper integrals, i.e. the infinite intervals. All right, so if the integral from a to t of f of x dx exists for every t greater than a, then the integral from a to infinity of f of x dx is equal to that limit as t goes to infinity of a to t of f of x dx, provided that the limit exists and is finite. Because if it's not, then you have a divergent integral, which will happen. So just think about this when we looked at the one we just did. So we had some a value over on the left, right over here. And then what we did was we found the area to the right. And even though it went on to infinity and beyond, as Buzz Lightyear would say, even though that happened, it became a finite number. So we had a finite area in here. Right? Okay, so that's what we're talking about here. We're taking the limit as t goes to infinity of the integral from a to t. So you're letting t get larger and larger, and you're finding the area. Now you could of course do it in reverse. So you could have the curve look like this instead. Right? In which case, then you're finding the area over here. Right? I guess I'll call this A. I think I'd prefer that as black. There we go. All right, and so then we could have that area, right? So you're taking the limit as t goes to negative infinity. So you're going that way, right? So you're taking that limit as t, and t is the bottom part of my integral because I'm finding the area from the left to the right, but of course that left-hand edge is heading off to infinity. And again, provided that the limit exists and is finite, hopefully. If not, then it's divergent. Okay, so then what I also could do is, I said the pièce de résistance, doing negative infinity to infinity. Now, when that happens, what you'll have to do is split it at some constant. So let me just make up an example here. So I have this curve, goes like that. And what you'll do is you'll split it at some value. It doesn't really matter what value. It could be positive, it could be negative, it could be 0. 0 is actually a very common one. But you'll split it. And then what you'll do is you'll find the area from negative infinity up to c, which would be this, using that limit argument. So you'll have one limit for the one on the left, and then you'll have another limit for the one on the right, over here. Right? So you take the pink left portion plus the green right portion, and away you go. Right? Now, in case 3, both integrals are required to be convergent in order for the overall integral to also be convergent. So if you want this to converge, you need this to be finite, and you need the other side to be finite. That's what they're saying, right? To make it work, they would have to be a finite number plus a finite number. So this piece is arguing right here. Both integrals must be convergent. So what that means is that you would need it to be something like, I don't know, if I pretend that this side over here was equal to capital A, and this side over here is equal to capital B, then I would say that it's A plus B. I could say it right here, actually. A plus B. Right? They would have to both be finite. Well, let me put it this way. This one has to be convergent, and this one has to be convergent in order for the overall thing to be convergent. So both must be finite so that the integrals are convergent, so that the overall integral is convergent. Right? That's what they're saying. right? You have to have finite numbers for both the left half and the right half, so that each integral is convergent, and therefore overall integral is convergent. Right? So you must have both integrals, or so both these values must be finite in order for each of the integrals they were representing to be convergent. And therefore, if both of these are convergent, then the overall integral is also convergent. That's what that's saying. Now, let's also remember that if either one of them is divergent, then the overall is divergent. So note, if you'd have infinity plus a constant, or if it's infinity plus infinity, right? These are all divergent. Right? So if this one's convergent, but this one's divergent to infinity, that's a problem. If this one diverges to infinity, but this one converges to b, that's a problem. And then if they both are divergent, that's also a problem. so all these cases would be divergent, and therefore the overall integral would be divergent. And again, the overall integral would be from negative infinity to infinity of f of x dx. That one. Okay, so let's put this into practice a little bit. I have a feeling some of these are not going to work out as nicely. Okay, so for this one, this is the limit as b goes to infinity, or again, t, you can use any letter you like. Limit as b goes to infinity of the integral from 1 to b of x to the negative 1 dx. Yes, you do have to write the limit b goes to infinity here and put the b up there. You cannot just write infinity. That is wrong. Because infinity is not a number. You can't substitute in something that doesn't really exist. So you have to take the limit. All right, so the integral of x to the negative 1 would be natural log of x. Natural log of absolute value of x, as a matter of fact. So natural log of absolute value of x, I'm going to take that from 1 to b. Right? So I still have b in there. B is going to be heading towards infinity. You cannot put infinity up here. It has to be written like this. Infinity is not a value. So this is the limit as b goes to infinity of the natural log of b, absolute value, minus the natural log of 1. I don't need the absolute value because 1 is positive, so I don't need to worry about it. I mean, if you want to put the absolute value of 1, knock yourself out. But all right, so that's the limit as b goes to infinity of the natural log of b minus 0, because the natural log of 1 is 0. Okay, so now I'm going to substitute. That's the natural log of infinity. And if I look at this value right here, I'm going to substitute it in for a second. Well, the natural log of infinity is infinity, right? I mean, you're making it slightly smaller, but it's still infinitely large. And therefore, my overall value is infinity, which means that my integral, let me box that. The integral I was given, which is 1 to infinity of dx over x, is divergent, which they asked us to find. They asked us to find the integral or explain that it's divergent, right? If it's convergent, find its value, but it's divergent. All right, let's do it again. So we have the integral from 2 to infinity of dx over square root of x. Remember, that's x to the negative 1/2. So this would be the limit as, I'll use t this time. T goes to infinity. The integral from 2 to t of x to the negative 1/2 dx. Right? And then that would be the limit as t goes to infinity. And I'm going to integrate this. The integral of that would be 2 over 1 x to the 1/2, right? Because you add 1 to the power and then multiply by the reciprocal of that power. And you're going to take that from 2 to t. So this is the limit as t goes to infinity of 2t to the 1/2 minus 2 times 2 to the 1/2. Yes, you could factor out a 2, in case you're wondering. I just didn't bother. So that's the limit as t goes to infinity of, that's 2 square root of t minus 2t minus 2 square root of 2, which is what I was thinking of when I was writing that. All right, so let's put infinity in. So when I put in that infinity, that would be 2 times the square root of infinity, right? Just thinking about this logically. You're not really like substituting. You're kind of more pondering this. The square root of infinity is infinity. So this is infinity minus a constant. And infinity minus a constant is still infinity. It's not an indeterminate form. So this is infinity. And therefore, the integral that we were given from 2 to infinity of dx over the square root of x is divergent. And we can kind of put this all together because I don't know if you've noticed, but the examples we've done so far are related. So looking at the first one, it was, don't worry about the constants, it was 1 over x squared, right? And then this one was 1 over x, and then this one was 1 over x to the 1/2, right? So let me just make a little note. This one is the integral from 2 to infinity of dx over x to the 1/2. And we're learning something about the powers and how they all come together, which is on the next page. Now this one was example 1, it was 1 over x squared. This one was example 2, which was 1 over x. Remember this one, even though that's that area, this one was divergent and this one was convergent. This was convergent to 1. This one was divergent in the middle. Now the reason I said, well, I'll just say it's divergent, right? It was infinity. I guess I can put that. I'll just put infinity. Infinity is divergent. Oop, if I can make an infinity symbol. Yeah, that's a little better. All right, so that was divergent, even though the areas look very similar. They're not the same. And the reason I say ish on this one is because I'm not actually starting at 2 the way I was in that problem. And the trick is that it doesn't matter what value you start at, amazingly enough. The constant doesn't make any difference. So that's why it's ish, because the lower value, the lower limit is not 2. But the theory still holds. So it doesn't make any difference. And this was also divergent. So let's compare those 3 on the same Desmos graph and see what's going on. Amazing, isn't it? Okay, so when I had the first one, which is the one you're looking at, that purple one, that one was an area of 1. But then, I'll trap that off. When I let it go to 1, which is that area under the red curve, it was divergent. Just that little bit extra you're seeing there makes it infinitely large. Amazing, isn't it? And then the half is even bigger. And it doesn't matter if I start at 2, it still would be infinitely large. Fascinating, isn't it? So there's a cutoff point. There's a cutoff point because down here it was convergent, but up here it was divergent. Oop, and then it was really divergent. All right, so there's a cutoff point, and the question is, where is that cutoff point? And that's what the theorem on this page is giving to us. Right, so 1 over x squared was convergent. These are divergent, and they're so close, so close. And the answer is that it converges if your power, your p power, these are called p functions, right? So if your p function, if it's convergent, p for power, right? It's not really a power function because power functions are not in the denominator like this. So it converges if your power is greater than 1, say like 2, say like 1.5. That would all be convergent. And it's divergent once you get p greater than or equal to 1. See that? The or equal to. So actually it's this middle one here that's the cutoff. From this point on, it will be divergent, right? If I let that power get anything smaller, like a half, which it is here, it will be divergent. And if you notice, the constant at the bottom doesn't make any difference. As long as the constant's positive, the constant is irrelevant. It's arbitrary, right? It can be anything. It could be 2, it could be 3. That's why I let that one example have a 2 in it, because it didn't make any difference. Now, why is this happening? Well, I'm describing it right here. Basically, you're trying to get the function to go to 0 fast enough that it can overtake the fact that you're heading off to infinity and converge. So when we look at this one, that red line right now, that's the borderline. Anything at that level or above, right up here, would be divergent, right? It's not going to 0 fast enough. It's going to 0. I mean, you can see it. The limit of that is 0, but it's not going to 0 fast enough. But if I get x to, or the power, p power, to be larger than 1, anything in here, once it's above 1, it's going to 0 so fast, and that it, even though you're accumulating to infinity, even though you're adding up that area going to infinity, it's gone to 0 so quickly. It's gotten so tiny so fast that it's not going to matter, and it's going to converge. Amazing, isn't it? Just one little slider bar, and it can affect your answers so drastically. And by the way, this idea will come back in chapter 10 and 11 as well. This particular function, as a matter of fact, will come back in chapter 11. It'll be called a P series then, and we will see more about it then in chapter 10 in particular.